Now, next topic is blocking collectives. So, and if you remember my little cartoon from the very beginning, collective communication is what we've been doing the past day and a half or so. Yeah, I am broadcasting or multicasting information. I am the source of information to all of you. All of you get the same information. So what collective operations are, first, the term collective is they involve a group. And in like a group, not only a group, actually they involve a communication context. And that means all processes in that communication context, which is in MPI the communicator. Yeah. So if you want to have this type of communication in a smaller context, not all the processes, then you need to create a smaller communicator from a subgroup of a larger group. And we'll see how that works later on. So in a collective call, all the ranks must call the same operation for this to work. So you can't just have some call this function and then others call this other function. And like the more technical definition is, for collective communication, all on this specific communicator, all processes need to call the same sequence of collective operations. Yeah, and you need to make sure that, especially if you have collective communication in different subgroups, that not one process is involved in a communication on a different communicator, while it should actually participate in this other communication on another communicator, because then you will have a deadlock again. So, and you should only be in one collective communication per MPI rank at the same time. That means if you at some point use MPI thread multiple for multiple threads in a hybrid setting calling into MPI, you need to make sure that you don't have multiple threads calling into this collective communication. And that is, I think, partly due to potential shared state in the collective communication subgroup. Okay, then what is very, we'll say, very important, or what is stressed in the MPI standard, is that synchronization behavior is implementation specific. There's only a single function that is explicitly synchronizing all the processes, and that is called MPI barrier. We're going to get to that in a minute. Any other collective communication function in MPI may or may not synchronize, although some, it is kind of implicit that they synchronize because of the communication pattern that they use. Yeah, for example, well, I'll get to the, I'll point that out when I get to the explicit function then. Okay, so, and what they do, what collective communication in MPI actually is, they implement common data distribution patterns, like the broadcast here, into basically a high-level interface, so you don't have to worry about the best strategy for distributing the information. So the semantics in the MPI standard is mostly you have this data on one of the processes, or on lots of processes, or on a set of processes, and you after the call you want to have it in a different state. You want the same data to be on different processes, you want different data to be on different processes, you want everything to be on all processes, or so, right? And that's what the different functions do. Even though we have in the exercises, you will re-implement the naive version of those calls. So you will kind of re-implement a naive broadcast or a naive gather. You will learn on what those names actually mean. Don't take that as, oh, I learned how to re-implement this, so I'll do this in my production code as well. No, the idea is that you kind of get a feel for what is the data distribution pattern, and after that, you use the collective function call instead. Okay, so let's dive in. MPI barrier is the only collective synchronization functions. The other one is a the other ones are collective communication functions, because barrier actually doesn't communicate any data. It just is a barrier. So, and the general idea is that to achieve this, yeah, it basically, this needs to tell those two processes that it's there. This needs to tell those two processes that it's there. Actually, this should also tell these others that it's there. So there are some arrows missing in this picture. Okay, yeah, okay, those are that. So that is actually an animation problem. Okay, so the idea here is, geez, this is a little bit broken. So basically, we have a start time here, and we have some end times, yeah. And basically, what the barrier just ensures is that there is some point in time where all the processes involved are inside this call, yeah. Some may spend a longer time in this call until this common everyone's in the call is reached, and some may spend less time in the call after that time, yeah. But barrier just ensures that there will be this time somewhere in the timeline where all the processes are in there. Okay, so what is this useful for? It's useful for benchmarking and putting output on like either the terminal or into an application to make sure that, well, this is the state where everyone is in there. Other than that, usually the synchronization that you have using like point-to-point or collective communication, this implicit synchronization between the processes due to the communication should be enough to write correct programs. Yeah, so you shouldn't start filling barriers everywhere. Yeah, because you learn, oh, well, barrier, I can synchronize things, and I need to, synchronize things before I go into the next step of my iteration. Well, all the iterations are independent of each other. Like the start of those are independent of each other in a way that the data is local. If the data is there, I can start. If it's not, I'm usually waiting in some form of communication call until the data is there. And that's the only synchronization I need. So you don't necessarily need to insert a barrier after each iteration or something like that. Yeah. So basically, remove that from your mental model on where to use this. So I'm coming from a performance tool background. So where we actually use this call is we want to make sure that we kind of measure this parallel work, the time that we spent on the parallel work. So if on the MPI init, it's a collective function, yes. And we have a time where everyone is in the call, but this is doing a lot of stuff before it's doing the parallel work. This one is actually also doing a little bit less, and this one is basically taking up all the time until parallel work starts. So what would be the time to measure? The maximum, then like this MPI init here, and that's the maximum time, but that's a distortion of my parallel work. Or should we have like the minimum, or what? Then I need to exchange data. So the easiest part is that I insert a barrier at the end of this. synchronize all of those, and then they all start with the parallel work with my measurement at the same time. Okay, so to go back a little bit, again on the call, as we see on the top right corner there, MPI barrier doesn't take any communication data, no buffer. It's just the communicator handle that it is supposed to use for synchronization. So the next one is broadcast. So now we're moving data, yeah, and it's basically the idea is to replicate data that's on one process on all of the other processes. So what's here is we have a data pointer, a count, and a data type. The data on, and we have now something that we call the root. Yeah, because we kind of think of this to be some tree-like communication pattern, or like the source of the data, and we have the communication handle. So on the root, because it's a data distribution from the root to all the others, the data pointer holds the data that is supposed to be distributed on the root. On all the other processes, this has to be a valid buffer of the size of this, but it doesn't, it will be overwritten in the process. Yeah, it doesn't have to be initialized. It will be overwritten with the data that resides on the root process. Yeah, again, we have this triplet of what do I want to communicate and from whom, yeah, is now a little bit easier. We see we do not have any tags, and the send buffer basically is the one at the root rank, and the receive buffers are the ones at the non-root ranks. Yeah. In principle, with all of these collective communications, the root is part of this, and so are all the others. We'll have to, I think it's in one of the later examples, don't do if-else things in collective communication. Like we had this, if my rank is this, then do the send. If my rank is the other, then do the receive. In collective communication, all call the same function. So everyone calls broadcast, even the ones who receive from the broadcast. Yeah, and you can't mix point-to-point and collective communication. They're independent of each other, meaning that you can have a non-blocking send going on while you have collective communication going on, and they don't interfere with each other, even on the same communicator. Okay, so one thing that is very important, because again, we have a count and a data type. Again, the type signatures must match across all data types. And one thing that is also very important, we had this, the receive rank on the point-to-point communication was allowed to have a larger, or specify a larger buffer. Here, with collective communication, the sizes have to fit. Yeah, so what you send needs to be what you specify to be sent needs to be specified to be received. Okay, and the communicator, as I said, is the communication context. So let's have a look at this data distribution pattern. So we'll see many of those squares with the other functions as well. We see these squares, and we have the ranks here, so that's with like rank 0, 1, 2, 3, and we have the data here with first element, second element, and so on. So here is a very light blue first square, and after the broadcast, we have this square basically replicated here, and this is it's not overwritten because we only have one buffer, yeah. So it stays in there, Yeah, so if you implement this, usually you don't need to send to yourself. So send to yourself is a special case that you should then handle appropriately. Okay, so coming to the examples of things you should do and what you shouldn't do. Yeah. So first of all, what you can use this for is, I said, some of the like standard input is only given to the first rank, right? And all the others need to understand like what the elements were. So you read things from the user and then broadcast that to everyone else. So what it does, MPI broadcast this value here, which is one MPI int. That was the root. Root is me, it's 0 on MPI world. So it basically involves all the other processes that I started. And that's a common way of using or starting up things and communicating like configuration, application configuration to other processes. Okay, so what would be wrong is that just the rank 0 is reading the value and then broadcasting it, and all the others don't do anything because they're not broadcasting themselves, but they are part of this communication, right? So they have to call this too. So even though you should never show wrong examples, this here should be just a reminder on how not to do it. Okay, so and that is already the solution to exercise 1 of your collective exercises. We have a simple broadcast. We have the data pointer. We have a count at the data type. We have a root. We have a communicator. We determine the rank and the size, like my personal rank, so I know who's the root or whether I am the root. And then I need to know who else, how many other messages I need to know, I need to send. Then if I am the root, then for all the processes, if I'm not the root, then send to that process. Else, everyone else is receiving the data. So that's the naive implementation on how to do that. Any questions to this? Again, disclaimer, do not ever implement a broadcast this way. Okay? Okay, so then the next one is called scatter. Again, we're talking with collective communication, we're talking about data distribution patterns, not about algorithms. The algorithms are implementation-specific information that you shouldn't have to worry about as users of MPI. So here, what we want to do is a one-to-many data distribution. So one has the data, and instead of replicating, we want to chop that up into different chunks and want to distribute the chunks to the other processes. Yeah, and that's what scatter does. We kind of have a send buff, a send count, and a send type, and we have a receive buff, a receive count, and a receive type. And evidently, the root process has a large buffer, yeah, that's much larger than like what the receive buff actually needs to be. Right, because that's the large part, and the received part is the small part. To make it easier for your mental model, is the buffer needs to have everything allocated, but these two define the specific data exchange type signatures. So this is not the type signature for the whole buffer, but for a single block to communicate, and evidently on the receive buff that is also a single block to communicate and to receive. So it's much easier in your mental model to bring those the send type and count and the receive type and count to fit together. Okay, and here the send buff itself and the send count and the send type, they're significant only at root. That means you can you don't have to allocate buffer space for send buff on the receiving processes, especially because this is a large buffer. You don't want to allocate that everywhere. You just want to allocate that where it is needed, where it's already there, right? You only want to allocate the receive buff everywhere. So also the others, they don't need to provide a send buff. They can specify null. One thing that we just stumbled over, a colleague of mine did that actually. There is an interesting thing about the C standard. Now, it probably is the same for Fortran as well, but I didn't check that. So what the C standard states is that if you pass a variable, an uninitialized variable, by value to a function call, then that results in undefined behavior. Yeah? So you might think, oh, this is significant only at root. I defined a send count because I have to define like a send count or a variable, but you don't initialize it. And you pass it here, then even though MPI will not evaluate this, the compiler is allowed to do all sorts of freaky stuff because it's undefined behavior by the compiler. And we have seen interesting optimizations with this significant at root where you think, oh, I don't need to initialize this because it's only significant at root. MPI can't do anything about it. It's a compiler thing and on the language level. Yeah, never pass any undefined value and undefined uninitialized variable into a function by value. So what you can do and should do is so you don't want to get into this if-else thing. It's like, oh, now I have to put send buff null. Instead of send buff a null, and on the root, I have to actually specify send buff. Now you have this, if I am the root, then do this broadcast. If I'm not the root, then do this other broadcast. That is ugly code. So what you should do is declare send buff equals null, send count equals 0, and MPI data type equals whatever the type is, or MPI data type null, whatever, but a specific value, a defined specific value. And then you do, if I'm the root, allocate the memory, set the send count, and set the send type. Because then it doesn't matter what those values are, but they are specific values. Yeah, and then you can use the broadcast on all, because on the root, the buffer is allocated, and all the rest is done. On the receive side, you'll have to, those things are actually not evaluated. Okay? Good. So then the send buff has to be large enough to supply the send count elements of data to each rank in the communicator. So think of this buffer has to be large enough that this times this is communicated to everyone in COM, including its own. Because with all of the collective communications, everyone is taking part. So in the receive buff, there's also one little tiny bit in receive buff for the root process. No? Okay. Data chunks are taken in increasing rank order. That means rank 0 has the first chunk, rank 1 has the next chunk, and so on. And root also always gets a chunk. And root doesn't always have to be 0. Yeah, so root could be any of those, any valid rank in the communicator. So again, the type signatures must match. Yeah, and I'm always puzzled. So this is also like a LibreOffice PowerPoint thing. So this is not supposed to be an envelope. I think it's an arrow. It should be a lookup data type. Anyway, so the type signatures, again, they need to match. And for your mental model, as I said, these two and these two need to match. Okay, so let's look at the scatter. We have on rank 0, for just simplicity now, this is our root rank, it's rank 0, and has 4 different chunks. And the send count, send data type would be, this is send type, and count is 1 in this example, right? So now after the scatter, now the receive buff looks like each has count 1 of those elements. And now these could be bigger. Yeah, think of this being like a row type or so. And now then each process gets a full row. Yeah, that's just, it doesn't always have to be a single element. Just the type signatures need to match. Okay, so send buff is only accessed at the root rank. Receive buff is written to by all ranks, even the root rank. And as an example, so you have the big data, again, like a 10 by 10 elements. We have a buffer that's big data. Here, it's allocated on all processes, but ideally, you do not want that. It's just for simplicity in this example, it's even 100 elements on the stack. And then you communicate big data, but only one chunk, 10 elements of this. And to the local data, 10 elements of this as well. Those signatures match. 0 is the root rank, and ComWorld, the communicator. So gather is the other direction. I have the data everywhere in small buffers. I want to gather the information on a local buffer. Yeah. Now, the receive buff is significant only at root, because only the root rank needs to receive something, yeah, semantically. And again, the same thing, the receive buff must be big enough to hold all the elements of receive count and receive type times the number of processes in COM, including the root. Again, root also receives from itself, so basically that's just a memory copy. And again, the data chunks are in increasing order. So in the receive buff later on, rank 0 data is at the very front, then rank 1, rank 2, and so on. Type signature, again, needs to match. And visually, we have just, the squares reversed from what we had before. Now we have things scattered across the different processes. After calling gather, the receive buff holds all the data. So this is really the inverse of the scatter function. Then there's something that's called all gather. And what that means is, as a result, so I do a gather, but the result should be shared with everyone else. So at the end, receive buff should be the same on all processes. What that means, all buffers need to be the size to hold all the gathered data. And when we see, we don't have a root process anymore, because we are collecting on all of the processes and not just one. Yeah, so there's no root rank, and each rank receives one data chunk from itself, and the data chunks remain, again, in increasing rank order. Type signatures must match, yeah? And so this is kind of logically, you can implement this by doing a gather first and a broadcast afterwards. Yeah, because that's the same data distribution pattern. But there are more clever ways to implement this. again. Yeah. And okay, so we have all of this results into all of that after an all gather. So, and then there's also, so the all gather is more of like collecting and distributing again, or directly, you know, gathering on all the processes. Now, but what we saw is everyone has the same data at the very end. Yeah, the next one, all-to-all, is basically like a whole bunch of point-to-point communications in one call. Yeah, you again have a send buff that holds kind of like a scatter-like array, so it holds chunks of things that you want to distribute. You want like a send count and send type. Again, this is for each individual communication to each of the processes. And you have a communicator. And so each rank distributes its send buff to every rank in the communicator, including itself. Yeah, and this way, I think it's easier to actually see with a visual representation on the next slide. So data chunks, again, are always in increasing rank order of the receiver's rank. They're stored in increasing order of the sender's rank, and almost equivalent. So, you know, those two ranks, because they're in the same communicator, they have to be, they're not the same, but they are relative to the same communicator. So this is almost equivalent to a scatter and then a gather, but not quite. So it's just almost, and it's basically here what you what we'll see here in a moment. So we have all of this data here. So at the very end, we end up with this. And there's also something. So as you can also see, this is also some form of a transformation, and that's why you, like a matrix transformation, that's why you often have an all-to-all communication in all of the distributed Fourier transforms, fast Fourier transforms, and the libraries that implement that. So they all, I think they all involve some form of all-to-all communication at some point in their algorithm. Yeah, so this one is distributed to all the other processes. Yeah, this one as well, and so on. Okay, so this is all pure data distribution so far. And now we have something that's called a reduction. And a reduction means I assign an operator to my data that I want to aggregate things with. So now again, we have a send buff, we have a receive buff, we have a count and a data type. And now we have something that's called an operator. We again have a root rank and a communicator. So what we see is the send buff and the receive buff. The send buff is significant on all the processes. The receive buff is only significant at the root. Yeah, and the receive buff will later hold the result, the aggregated result of send buff. Yeah. So again, the count and data type signatures must match, as with all of those collective communication calls. The operator is what's called a reduction after that in the latest standard, we actually said those are not operations, because operation is actually another defined term. So it's a reduction operator handle. Yeah, just to avoid that confusion. So I'll have to update the slides there. So we have a destination rank. That is where the data is aggregated. And we have a communicator with like who is involved. So the result is computed in or out of order depending on the operation. That means if we have the operator sum, things are added up, and depending on whether you want to have, or whether that's a commutative or not operator, MPI is allowed to do things in or out of order. But remember what Ruud said at his session. On paper, it doesn't matter. In a computer, it actually matters what you, in the order in which you add things up in a reduction. That usually implies that if you, so you have associative and commutative as characteristics. That means they're allowed to change order. That means that you're not guaranteed to get bit identical results, specifically not across platforms, potentially not even across, on the same platform with different number of processes and things like that. Yeah, because the ordering might actually change depending on where the processes are and so on, and that's how they are aggregated. So, yeah, beware of the non-commutative effects on loads in your process. So there are predefined operators. You can find out the max, the minimum, the sum, the product. There has been debate on deprecating this because it's, let's say, applications of product are rare, but it's there for completeness. And we have a logical AND, we have a binary AND, we have a logical OR and a binary OR. And there are some more, and you would have to consult the standard for getting the whole list. But you can also define your own, which would then be a callback function that you define that gets like 2 buffers, and it implements whatever you need to implement. And that callback function is then basically called by MPI on your behalf, on your data, like doing the things. And then you could implement your in-order commutative sum. Okay, so I love the symbols. Okay, so this actually should be like an operator symbol with a plus sign in it, and it's just hilarious. Yeah, greetings, shout outs to LibreOffice there. Anyway, so you can have a longer reduction operator, a longer buffer, yeah, and then element-wise reduction on this. So imagine this to be MPI sum. So it's 1 plus, okay, this should be 10 plus 19 plus 28 is 58. Yeah, 2 plus 11 plus 20 plus 29 is 62, and so on across the board. Yeah. So what this reduction is good for is computing things like how large is the error across all my processes of my algorithm, right? And then the question is it enough if just one process knows about it, or should all the processes actually know about it? And then, of course, there's something like allReduce that implements like a reduce plus broadcast, kind of. But there are also more clever ways to do this. Yeah. So, again, with the all function, no root. And yeah, okay. So we're almost at the end of collective communication. So yeah, so this is the allReduce where we have, yeah, basically the idea is the reductions that we had before are at the end available on all the processes in the communicator. Okay, so the advantages of collective communication as a summary from what you have heard so far is they implement some form of communication pattern, of data distribution patterns, yeah, and pick the one that you need. There are specific implementations that affect performance, but they all have the specified semantics that is specified in the standard. Yeah, so the standard does not mandate implement this as a binary tree or a binomial tree algorithm. Yeah, because that might not actually be the best for a certain situation. And so that is something that the implementation, MPI implementation, can decide. And for example, in the broadcast, the naive implementation, right, looking at exercises, would be this. So that is O of number of processes, complexity and the number of processes. So the smarter one is actually using some form of tree algorithm. And there are also, some are better than others. And the genius would be O of 1, where you can look up pipeline segmented transport. That is for super huge buffers, like thinking about, I need to broadcast a gigabyte of data. Yeah. Then basically this is some form of this naive implementation, but in a pipeline, so that the beginning of the pipeline and the end of the pipeline is small, and just gives you, and is much smaller than the rest of the transfer time that you have. So but then again, you shouldn't decide on what is the best algorithm for this, because you're not the algorithm expert, or you shouldn't have to be. Yeah, so you rely on the implementation to do the right choice. Okay, so in summary, in collective, if anything is named collective in the standard, all the ranks must, in the communicator that's specified with that, need to participate in this function. Yeah. What you need to check is the significance of arguments for specific calls. Yeah. Sometimes they're not significant, so they won't be looked at by MPI, but always make sure that they have some specific defined value to avoid some interesting compiler behavior. So the sequence of collective calls must be the same on all the ranks across that communicator. So you can't have some call a broadcast and then a reduce, and the other one call reduce and then a broadcast. That will fail. Barrier is the only MPI collective that is explicitly synchronizing, because that's its job. But some may synchronize implicitly, like the all gather and all reduce, and the all to all as well, just because of the semantics of the data distribution pattern. As I said already, the communication paradigms themselves, point-to-point, collective, one-sided communication, file I/O, all of these are independent of each other, so they don't influence each other in terms of correctness. Yeah, of course, if they use the same medium, like the same network cable, they share that medium, so performance-wise, there might be an impact. But you don't have to worry, can I send this and then, can I do an iSend and then do a broadcast? Will that interfere? No. So MPI will take care that those two things are on different communication context in a sense.